Some new material uploaded for these fellas. I'm going to go through and hopefully fix what was wrong with the previous one, the audio, for the reliability sort of presentation I've done. So what we're looking to have a look at is a couple of things here. We're going to look through the T-lock example. We're going to look at reliability measurement systems, the PDF. We're also going to look at the Word document of reliability, and then start to cover some of the systems incorporated in a measurement system itself. We'll look at some of these other ones and maybe do it within this one lecture, or probably do it in a separate one, to be honest. Just as a side note here, down some of these other PDFs are sort of further reading for you that go a little bit beyond basically what we're going to cover directly through more direct notes pertaining to the questions that you could possibly face, for instance. But there is other, as I say, other notes down the bottom here, for instance, where you'll be able to obtain more information from. One of the ones we'll look at here for first and second order systems are going to be through this particular instrumentation and control, one from Free Study actually. It's an old HND unit of instrumentation and control. It's never been actually taught in the college itself, but one of the units within it is very applicable to mathematical modeling, so that's why we use some of the tutorial stuff from it. So it's a good one to read over actually, the instrumentation and control, tutorial 3, models and calibration. So what I want to start with is the reliability one, which is number 10. We'll just begin here if I open this up. So we should be, I think, on the correct reliability one. Yep, the wee red border. So I'm not going to go over, as you might have heard from the first video, if you listened to the first sort of 9 minutes of what was actually, well, listenable, I suppose. But I'm not going to go over each individual point here. I'll talk about different aspects of it as we go along. But it's there for you to read aside from the standard class time, effectively. So when it comes to characterizing the reliability of a measurement system, or for instance a particular element, so a standard measurement system, as you'll see later on through some of these other Word documents, they're actually made up of different sections or elements. You have to answer the question, says here, what is the probability that it will keep working faultless for a specified period of time? And we can do calculations based on that, and these type of calculations are all the type of things that are used to help determine warranty period for sensors and other consumer products, pretty much. So we're all used to purchasing products that usually come with a year's guarantee, for instance, to operate fault-free for the length of time. And obviously if we develop a fault within that particular system, we would expect then a replacement or repair free of charge. And this basically is the strength of the reliability that the manufacturer has within their product. They go through a testing phase, and we'll do again more calculations based on those, and we'll see how we will come up with reliability percentages for measurement systems that we're applying ours to, and how that can then be applied to, for instance, warranty periods and the T-lock, which is the lifetime operating cost. So the issue of reliability is important as that of accuracy. How accurate something is, basically how long it's going to last and do the same thing for over and over again. Sort of relates a little bit into repeatability as well, how reliable something is. One can have an instrument that is very accurate, however, if it keeps breaking down, then we have a problem. And obviously you can say it the other way around as well, that it's very reliable, it keeps giving you a reading all the time, but it's not a very accurate reading. You know, one's as bad as the other. So we propose to examine the issue of reliability of measurement systems in some details in the following sections, with a view to enable both designers and users to make informed decisions, which is to be the T-lock example, when designing and choosing each of these systems. So a very quick overview, and I know it's a wee bit sort of grained here, it's not just as easy to see, but you've got your chart here plotted against time, and up the y-axis is reliability from 0 to 1, as in perfectly reliable. And you'll see that it sort of has three main sections here. Section number 1, beginning at the very far left hand 0 point, is basically the beginning of time for that particular sensor or measurement system. The second dashed line, or the first dashed line in the second section, is a calibration point in which the system has been recalibrated or something tweaked in it, maybe for instance, to make sure that it's still operating the way it should. And then obviously there's a third one there, but what you should notice here is that each time it's calibrated, the slope of how reliable something is of a greater gradient each time it's calibrated. It's mainly down to aging and other faults, similar to the problems of having things running for long periods of time. So you have your reliability, which is denoted by R of T, and then the unreliability, which is the F of T. Try not to get that confused with a failure rate, which you'll see coming up later on, but rather reliability and unreliability. It's hard to sometimes get your head around the F being failure, but it's not really quite that, because you see it's defined as something else later on as well. And what we can notice here, that a system is either reliable or it's unreliable. It's one or the other. So we can deduce from that the RT plus FT will equal 1. And a definition basically of reliability can be defined as the probability that an element will operate to an agreed level of performance for a specified length of time under specified environmental conditions. So those specified environmental conditions are sort of basically the get-out clause for a lot of manufacturers. It's the standard conditions things should operate in, usually defined like humidity, altitude, amount of shock vibration that it's allowed to work under, maximum minimum voltages, length of time operating for, things like that. And so for instance, if the probability of a thermometer will measure temperatures with an accuracy of plus or minus 0.01% over a range of -40 to 100 degrees Celsius for at least a year is 95%, then that instrument has a reliability of 95%. So you can see that the reliability and also the availability, which we'll see later on, is measured as a time period of a year for those specified conditions of operation and over that horizon of 1 year. This gives rise to the concept of unreliability, which is the complement to reliability, obviously, which can be defined as the probability that an element or system will not operate to an agreed level of performance for a specified period, subject to specified environmental condition. Now, obviously, if you go outside those environmental conditions, then it's not really within the standard reach of the calculations of what a manufacturer would do, and it's a great get-out clause, as I was saying. So if it's operated and temperatures too high for it, then it's down to your own fault that you've damaged and operated outside of those principles. You void the warranty. And here, just sort of confirming again, so the sum of RT and FT is 1. So basically there's a 100% chance it's either going to work or it's not going to work. So when considering the non-repairable items of a measurement system, so for instance one that's just discarded, thrown away once it does develop a fault, has to be taken into account the mean time to failure, or MTTF. There's going to be a few of these coming up, this type of mean time, or to, or between, and they're all sort of denoted by their contracted form of initialisms of MTTF, MTBF, and so on. There'll be other ones you'll see later on as well. So the latter of the MTTF is approximated by carrying out survival tests. Basically it's used until it breaks on a certain number of test items, and the average survival time is then the mean time to failure. And the inverse of the latter is the estimated mean failure rate, which is lambda bar, which is a wee flat symbol above the lambda, expressing the average number of faults per year. So if you can calculate the mean time to failure, then you can automatically, by taking the inverse of the answer, find out lambda, the mean failure rate. So remembering here that the mean time to failure is the amount of time until it breaks of a certain system on how many different items that you perform the test on. So in the case of repairable items, it's slightly different. The metric for the reliability of a measure system is the mean time between failures, because obviously it's each time it breaks down, what is the time between each breakdown effectively, because you're obviously meant to go in and repair the item rather than discarding it. So the latter figure is estimated by carrying out usage tests similar to before on n items for a certain length of time. If the items collectively develop nf number of faults, which take tdj to fix, then one can determine the mean time between failures rather. And the one way to do this is to calculate the mean downtime, which is simply the average of the set of times it took to repair the faults. Multiply the mean downtime by the number of faults to obtain the total downtime, which you've sort of already figured out by doing the top section anyway, and then subtract the above figure from the total test time. This incidentally results in the total uptime for all the items under test, and then is divided by the NF, the number of faults, or failures rather. So in the case of repairable items, the mean failure rate lambda bar is simply the ratio of the number of faults to the total uptime. So in other words, it's the inverse of the mean time before failure, or between failures, sorry. Keep always getting that one wrong. Furthermore, the concept of availability, which is A, can be used to characterize the reliability of a measurement system or element. You can do each element separately and get a combined total, which would be the system. This is the average total time the latter is likely to operate fault-free out of the cycle, which is the mean time between failures and the mean downtime added together. The unavailability, therefore, is the measured proportion of time the system is out of order of the cycle time. A and U are then complementary, just the same as the way reliability and unreliability were complementary. Both availability and unavailability are complementary. So they should obviously add up to 1, usually expressed obviously in a percentage. Moving on down, the instantaneous failure rate, which is the rate of change of the probability of failure over an infinitesimal length of time, can be linked to the reliability, which basically the probability that a measurement system element will operate to a agreed level of performance for a specified period subject to environmental conditions. So remember that. Through the integral shown in the slide above, which is the previous diagram we had. So this relationship is useful as it enables the user to characterize the reliability of a measurement system using data obtained through testing. So the typical form of a failure rate is what's known as the bathtub curve. I'm going to see if I can hopefully draw a little bit here. And we will go with if I have a chart like so, and I want to then add in more squiggles, you basically have this type of idea here, meant to be flat to that bottom bit, something along those sort of lines, where we have 3 main areas, and I'll try and break that up sort of between here and also here. Now the drawing isn't overly accurate, but this one down the bottom was meant to be pretty much horizontal. And if I can increase the weight of that, something like that, there, bathtub curves, curves down, flat lines, and then rises back up. Not drawn very accurately, but you'll see it from future PDFs here. The bathtub curve basically shows the main three stages and elements of basically the life cycle of a sensor, in that you have from manufacture, install, and commissioning, where things can fail because basically it's being moved around a lot more, and if there is any faults in it, it's going to be discovered early. And at some point it settles down once it's fully commissioned, and you should have this relatively flat-lined linear response to time of a failure rate that basically says along any length of time here between first install and commissioning to a given point in time here, the instantaneous failure rate should pretty much be linear. And what that really relates to for calculation wise can be for a company warranty periods. So if they can do calculations to figure out how long in period of time this flat part of the bathtub curve would be, then they're able to then start specifying a warranty period, which obviously is sensible in the fact that one, they can still make money off it by selling the product, which is meant to be reliable, but also not cost them money in the fact that they put the warranty period too long into the tail end here, in that it's going to cost them too much from warranty claims. Moving on a little bit further, a couple of formulas here derived to do with instantaneous failure rate. So the period in the middle of the useful life of the product has a constant instantaneous failure rate. If one uses a relationship linking the instantaneous failure rate to the reliability, the latter can be written then as the reliability according to time is the exponential of negative lambda upon, or multiplied by time rather. Following on from that we know that R of t plus f of t is equal to 1. Rearrange, we can then get a formula for the unreliability according to time is 1 minus the exponential of negative lambda multiplied by time. So the subsystems. So a measurement system can and will typically be made up of a number of interconnected elements. Two basic configurations are shown, the figures are displayed here. Series and parallel. They're basically just obviously a row of systems, boxes with lines coming in and out, which is an input and output from a system, and they're all linked together in a straight line, which is the series version. And then you have at least one set of parallel connections. So you might have a single box leading into a second, which is also in parallel with a third, and then leads into a fourth box, which is in series with 1, 2, and 4. And then number box 3 obviously is the one that's in parallel around number 2, which gives you a pathway of either 1, 2, and 4, or 1, 3, and 4. So for a series system, reliability is comprised as a number of elements present increase. 4 elements combined in series with each a reliability of 0.99 for a given length of time yield a combined reliability for the same length of time of 0.96. So therefore the overall system becomes less reliable than the least reliable element within the group, and the resultant failure rate for the overall system is the sum of the individual failure rates. Then for a parallel system, that's a system which uses different methods in parallel to obtain the same output. So for instance, you might have a system that incorporates two measurement systems, for instance 2 thermometer readings that are able to display voltages in through to the rest of the system. Just in case one will go down, it helps with a thing called redundancy. If one of them goes down, the system as a whole still operates for a longer period of time. And this might happen if you have a part of the system that can't be made overly reliable. So for instance, if we take the example of the thermometer again, say the signal processing element from the measurement system, it's not viable financially to develop a more reliable version, but what would be more sensible for the company would be to put the same one they do have that isn't as reliable, but then put it in parallel with the same one, which then increases the reliability of the system using a thing called redundancy. So I've just went and changed the Word document a little bit here to include the bullet points that were in the image beforehand. And you'll see some of the ones down below. So design for reliability, element selection, so making sure you pick ones with well established failure rate data, so you know sort of beyond reasonable doubt how they should perform. The environment, minimum complexity, include redundancy, so being able to have things in parallel. And then a little bit similar to that is diversity, where instead of having the same element in parallel, you have two different elements, so doing the same job but via a different principle, maybe one measuring via a resistance, one measuring via a voltage differential. Throwing in down the bottom here the maintenance of reliability, to do with either preventative or just standard maintenance from failure. Choice of measurement system, and then this is really what we're relating and getting on to here, is the total lifetime operating cost. We're going to run through just in a wee second here. Once again, I'd open the TLOC, or total lifetime operating cost PowerPoint example, so hold on. So just before we move on to the TLOC example, show you some of the background reading material for number 11 here, the reliability of measurement systems. This is a PDF, it's a chapter out of one of the textbooks. So this shows you some of the more long-winded basically explanations of where some of the formula that we've seen is generated from. So we've got probability, we talk about then reliability, unreliability, and there's a first form of R of t plus f of t is equal to 1. So it's either obviously reliable or it's unreliable, it's one or the other. We've then got the formulas for ones that are non-repairable, moving on to the repairable items, the mean failure rate. Then we've got a couple of charts here relating to ones that are either repairable or non-repairable, depending on, so for instance there's two different downtimes here for this particular device, number 1, which then relates into the total uptime, downtime. Then you get the mean time between failures equal to total uptime divided by the number of failures, which is equal to MTBF, NT minus NF of the mean downtime divided by the number of faults, and giving you 7.7 for that particular one. There's the mean failure rate lambda bar that we talked about is equal to N of F over NT minus NF MDT. Obviously that's just the inverse of the one we've seen just above, 7.7. Moving on down, we've got the instantaneous failure rate that we chatted about earlier on, so the failure probability of the delta psi xi, unconditional probability of delta f that the item fails during the interval of delta psi is therefore the change in the failure rate probability that the item survives up to the time of psi as well. So not overly concerned about that one. Keep motoring on down. We end up with this one we were talking about a little bit earlier, to do with the graph, to have the interval then, or the integral rather, to find the area underneath. So this is the bathtub curve we spoke about, or the useful region is almost completely linear, a little bit of curvature at both ends there. We've got the wear out section and the basically the bleed in, or the early failure rate section, where it could be install times, commissioning times, delivery, all that would occur in that part of the life cycle. And then hopefully once it's installed and commissioned, you should be in around this area. It settles down and hopefully should be a linear useful life region of the sensor or measurement system, and then finally wear out. But what we're looking to skip down to here, there's some of the other ones just by the way we spoke about, with things either being in series or parallel systems, and the images that we spoke about. So ones here in parallel might all be doing the same function, so we have then in that term redundancy. But skipping on down, that we're looking for. Design for maintenance for reliability, we spoke to some of those, and there is the bullet point sections that the notes were derived from this chapter of the book, the element section, environment, and so on. Make sure we're not past the right bit. Choice of measurement, not quite yet. It's right down near the bottom. Yeah, total lifetime operating costs. So the total lifetime operating costs of a measurement system is the total cost penalty incurred by the user during the complete life cycle or lifetime of a system. So it's given by the initial cost of the system, which includes both purchase, delivery, any install and commissioning costs, plus the cost of failure and maintenance over the lifetime. So the lifetime might be obviously usually in years, could be 5, 10, 15 years for instance, plus the cost of measurement error over a lifetime of the system. So that might be, for instance, if you're having a flow meter, for instance, and you're measuring product that goes into a certain system, if you're constantly mismeasuring the amount of product going in and you're giving away too much product to what you're actually charging over the cost or over the length of time that it's actually operating, it will cost you money, obviously, over a length of period of time. So if you're actually pumping more, say, paint into the tins than what you're actually charging for, over a length of time, that costs you money. So there's other more long-winded formulas here showing you all the calculations that are required, but it's quite simplistic, so we want to break it down nicely in the example version. So I'm just going to get that open and going. So we have here, and we should be able to go main screen with this one. Yes. So the T-lock example. So as an example, we're going to be comparing two systems, System 1 and System 2, just the left and right hand sides of the sort of right part of the columns here. Down the left then is each of the individual cost items. You've got purchase cost, which is basically your initial outlay, 12 grand and 14.5 for this particular example. Delivery, two different prices for delivery, installation costs, and so on. You can read them yourselves. The bit we're concerned about that sort of makes things a bit difficult and different, I suppose, is the warranty period and the likely number of failures and the estimated cost to repair. Obviously, during warranty, the idea being that if the fault occurs within warranty, it should cost you nothing. Now obviously there's going to be losses due to downtime, which we're not going to take into consideration in this instance here. But if you have a life cycle, both of them are 10 years, you effectively have 9 years of where you pay for faults yourself in System 2 and only 5 years for paying for faults for System 1. So we'll run through the example showing you how to calculate them, and you'll hopefully get an idea of how each of them work, and then you can have an attempt at doing the T-lock number 2 yourself for system number 2 and see if you can come up with the same answer. Then we have to talk about justification and how you actually select the product over one over the other. So as an example here we have the and I just want to just pause for a second there and back on T-lock example number 1. So from the previous PDF we've seen that the T-lock was the purchase cost, delivery, installation, both commissioning, and the cost of all failures over the lifetime, and obviously the cost of any measurement errors over the lifetime as well. So hopefully this break it down nice and easy for you. So the initial purchase cost of the system number 1 was £12,000, delivery 2,000, installation 2 grand, commissioning was free, and then what we have to swap the last two around here. The cost of measurement errors was £2,000, and then we just need to add on the cost of all failures over a lifetime. So this is the bit that sort of is the main element of the question, I suppose. The first one said that it had 30 errors or failures over a lifetime, likely number apparently, over a lifetime. So if we have 30 failures over a lifetime of 10 years, that's 3 failures per year. And the critical thing is here, we're assuming that the faults occur in a linear fashion. So from install to end of life, 10 years from time, we are assuming that it has 3 faults per year. Now, this obviously, or usually, isn't correct in the fact that it usually ends up with more towards the end of its life cycle rather than at the beginning, spread over a linear region, which makes a big difference when we're using a calculation for warranty. We're going to stick with that method. We are going to assume for both of these and for any future questions that basically the faults occur in a linear fashion. Now, this may not always be true, but there's not much better data we can go on from this as well. So if we have 5 years of basically on-site free repairs due to equipment failure, that means if we have 3 per year over 10 years, we effectively have then 15 faults that are covered within the warranty and 15 faults that are not covered within the warranty. So obviously the first 15 are all covered by the company that you're purchasing the system off, but rather the last 15 from year sort of 6 to 10 is then going to be paid for by your company effectively. So we have £175 per fault, 3 faults per year over 5 years. And you see here on the next one, 3 faults per year, £175 per fault, which is £2,625 of errors basically that you, for your company, need to pay for that is outside of the warranty period. So T-Lock 1 was 12 grand, 2 to 02, and then obviously the faults comes to a grand total of 20,625. So I want you to have an attempt at number 2 yourself, T-Lock 2, just remembering that the system has obviously different purchase, delivery costs and so on, and the warranty this time is only 1 year, but the likely number of faults is lower. It's only 20 faults over a 10-year period rather than 30 faults over a 10-year period. So have a quick attempt. You can pause the video, have a go at it, and see if you can come up with an answer. So hopefully you've had an attempt, and we scribbled down at something there for the T-Lock 2. First bit pretty straightforward: delivery, purchase cost, installation, and so on, and a commissioning cost at £250. I think that was correct from the other one. Yep, it was. Just thought my ones were off. Plus the measurement error of 2 grand. And this time we have 20 failures over a lifetime of 10 years again, averaging 2 faults per year, and again assuming a linearity of faults over a life cycle. We would say that it occurs at 2 faults per year. Therefore, only 2 faults are going to be covered by our warranty period of 1 year, and the rest, the other 18, are assumingly falling within the 9-year out of warranty period of the rest of the life cycle, which comes in at 18 by £200 per fault, which is 3,600, and therefore that system then actually comes into £22,100. So we have T-Lock 1 at £20,625 and T-Lock 2 at £22,100. So there's not even 2 grand the difference there. And then you basically now need to justify which one do you choose. Is it merely just down to the final price, the total lifetime operating cost? So the formula is there for a reason. It does obviously give you a final bottom line figure as best as can be assumed for faults and maintenance costs, etc. over the lifetime. It's obviously estimated lifetime. We don't know exactly. It's going to be 10 years. But assumed from data collected by the manufacturer of whatever measurement system you're purchasing, you go on as much data as you can find. What other factors that you're provided with within the table might sway you one way or the other. So although T-Lock 2 has come in at a dearer price, you might say that there's other benefits. Now this system, the way it's set up in this question, may not sort of show that this is a better way. But you could say that the projected cost due to measurement errors over a lifetime is £2,000 compared to £3,000. And if you were to, for instance, maybe ramp up production at any point, that figure is more likely going to change, and that system 2 is going to increase more than what system 1 is, which might outweigh the final difference. You might also say that system 1 gives a cheaper outlay for purchase and delivery. So purchase and delivery becomes, let's see, what, 14, 16,000. And the, pardon me, sorry, just yawning. And the other one comes in at 16,250. No, a bit more. 250 is 16 and a half, sorry. Comes out at 16 and a half then. So that particular one is only slightly more. It's very little in this case. But if the difference between those two parts, so the top four figures here, the purchase, delivery, installation, and commission, if that was significantly cheaper, for instance, for system one, it's not very much. You might say that to do with budgetary constraints at the early part of the installation, basically, you may not have the capital expenditure to actually purchase system number two. There's only £500 of difference in this case, so it's not really a good argument in this one. But it could be that system one was the better choice because it's cheaper initial outlay of capital. Again, warranty is a big thing. So if the system does not, obviously then, as we sort of are assuming, has faults linearly, then the longer the warranty, generally then the more money you should save. In this case, your 5 years to 1 year. System one certainly is coming out a much better prospect here, but in any other examples you could play around, change some of the figures around, see how they come out, change some of the purchase costs down, so it might be cheaper to buy, cheaper to be delivered and installed, but you might end up with a lot more faults and a lot more cost per fault. So if you maybe had a cheaper system, say it was only 10 grand, delivery was free, installation was free, you know, and maybe only a 2-year warranty, for instance. So it could be a lot cheaper to outlay, but you might have 50, 60 faults over a lifetime. The lifetime might only be 8 years, and maybe say £200 to £300 per fault. It'd be interesting to calculate that out to see which one still works out cheaper over the total lifetime operating cost. But then really, which is the better system to have? So have a quick look at that, change some of the figures around and play with them. It would be good for an example. So guys, that's us back to there. I don't want to cover any more within this lecture. Make sure you have a good read at the number 10, just need to refresh that bit. 10 for reliability, read through each of those, reliability and measurement system. That's the chapter within a textbook which all the notes are sort of derived from. And the T-lock example, make sure you have a good look at that as well. So I'll sign off here and we'll have another look at some of the other elements here in another week.